Hi, welcome to the video on chain rule. Before I proceed, I just want to let you know something very important. That is, there are many ways of asking the same question in derivatives. For example, I could ask the question ddx of x square plus 3x, the quantity raised to 10, equals how much? Or find ddx of x square plus 3x to the 10. Or f of x equals x square plus 3x, the quantity raised to 10. F prime of x equals what? Or find f prime of x. And a third way is differentiate x square plus 3x, the quantity raised to 10. And in fact, there are even more ways. There are some people who use an uppercase D to indicate the derivative. Okay? Anyway, regardless of how this question is posed, there is one nice way that we can learn about chain rule. And what I'm going to do is use this ddx way of stating the question. You can always convert it into f of x is so much and what is f prime of x. Okay? Here is the idea of chain rule. d dx of x to the n. Do you know what that is? So this is the basic power rule of differentiation, right? Now the question is, suppose I know that d dx of x to the n is nx to the n minus 1. Would that help me find, this implies, that symbol means implies, d dx of f of x to the n would be. Now let me pause for a second. So what we know is d dx of x to the n to be nx to the n minus 1. But from that, could we figure out exactly what d dx of f of x to the n would be? And the answer is, yep, it's as simple as n times f of x to the n minus 1. So what seems to have happened? Instead of x, we have a x to the n, whereas we have a f of x to the n. And in the answer, we have a x to the n minus 1. Instead, we have a f of x to the n minus 1. As simple as that. However, there's one very, very important thing. And that is, according to chain rule, it's not enough if you say n times f of x to the n minus 1. You must make sure to multiply by f prime of x. That is the key. Okay? Now, what else I could do? In fact, this is, what is f prime of x, right? If that is your question, it's as simple as, in this notation of d dx, it's nothing but d dx of f of x. So once we know d dx of x to the n, we can find d dx of f of x to the n by using chain rule. Did that make sense? If it did not, don't worry too much. I'll give you plenty of examples and it should be crystal clear to you. What else do we know? The basic derivatives. We also know d dx of e to the x, for example, is e to the x. Now the question is, this implies, what if I don't have a simple x? Instead, I have e to the f of x. Well, the answer would be e to the f of x. Because d dx of e to the x was e to the x, d dx of e to the f of x would be e to the f of x. The only thing is, be sure to multiply by f prime of x. That's where the chain rule comes in. Okay? As before, I might prefer to write this f prime of x as d dx of f of x, and I'll show you why I would rather say d dx of f of x. Let's see if this concept is beginning to make sense via another example. What else do we know? We know the basic derivative d dx of sine x. d dx of sine x is cosine x. Now, can you guess what question I'm about to ask? I'm about to ask, I'm sure you guessed it, what is d dx of sine of f of x? I don't have a simple sine x, I have sine of f of x this time. And in the answer, I won't have a simple x, I will have a f of x. That is, I have cosine of f of x. But I cannot and I should not leave it like that. I must make sure to multiply this by f prime of x, or, like I said, equivalently, that's times d dx of f of x. Now, I sincerely hope you are getting an idea. What else? D dx of natural log of x. We know that to be 1 over x. So that means if our intention is to find d dx of natural log of f of x, then the answer would be 1 over f of x, but be sure to multiply by f prime of x, or d dx of f of x. Alright, we can, let me do couple more. For example, what is d dx of tangent x? d dx of tangent x is secant square x. That means, if I ask you what is d dx of tangent of f of x, then the answer is secant square of f of x times f prime of x, or let me call it as d dx of f of x instead of f prime of x. One last one. d dx of, maybe you should take this as a challenge. d dx of secant x is secant x tangent x. That implies d dx of secant of f of x is, now we simply replace the x with a f of x, right? That's what we've been doing. Secant of f of x times tangent of f of x times f prime of x, or d dx of f of x. Guess what? You just learned the chain rule. Well and good, but let's get to more practical problems. What's with all this secant of f of x to the n and all that? Usually problems are not given like that. The problems are given more in this form. That is, what is d dx of x cube plus 2x square minus 7, the quantity raised to 10. Okay. So the moment you look at a problem like this, you should say, does that look like, had this been x to the 10, let me put it that way, had this been d dx of x to the 10, you would know, oh, that's 10x to the 9. The derivative of that would be 10x to the 9, right? But it's not a simple x to the 10. It is something more complicated raised to 10. And because it's something more complicated and it's a function of x, you think of this as d dx of some f of x to the 10. Right? Now, as we said earlier, d dx of f of x to the n is n times f of x to the n minus 1 times the derivative of f of x itself. So applying that, 10 times this quantity x cube plus 2x square minus 7 raised to 9. Don't stop there. Be sure to multiply by the d dx of f of x itself. In our case, would you agree that our f of x happens to be this x cube plus 2x square minus 7. Now you see, this is why I don't say f prime of x. I would rather think of it as d dx of f of x, because f prime of x meaning times the derivative of x cube plus 2x square minus 7, it may not be that clear. So always, to me, this gives more clarity. Alright, so in the next step we will say this equals 10 times x cube plus 2x square minus 7, the quantity raised to 9. And now let's figure out what the derivative of x cube plus 2x square minus 7 is. At least in this video I am assuming that you would know how to differentiate simple and straightforward things like that. Would you say d dx of x cube is 3x square, applying the power rule? Similarly, d dx of 2x square is 4x, and d dx of negative 7 is 0, or minus the derivative of 7 is 0. And so here we go. This is the answer. 10 times x cube plus 2x square minus 7, the quantity raised to 9, times this. Cool. Let's pick another one. 2. What's d dx of e to the x plus sine x plus x square, the quantity raised to 9. Now, once again, does this look like f of x raised to a power of 9? So, the derivative ought to be 9 times e to the x plus sine x plus x square raised to 8, and times d dx of e to the x plus sine x plus x square. And this in turn is 9 times e to the x plus sine x plus x square, that quantity raised to 8, times the derivative of e to the x is e to the x plus the derivative of sine x is cosine x, the derivative of x square is 2x. There we go. We are done. Okay, let me make up another problem. 3. What is d dx of e to the x cube minus 2x square? Let me rewrite that x cube a little clearly. So d dx of e to the x cube minus 2x square. So e has been raised to the power of x cubed minus 2x squared. Okay. Now, to me that looks like it's not a simple e to the x, it is e raised to something more complicated. The moment you say something more complicated, think of it as f of x. Okay, d dx of e to the f of x. Now, that we said earlier is e to the f of x, that is e to the x cubed minus 2x squared, times the derivative of f of x itself. So be sure not to stop with e to the f of x. Be sure to multiply by d dx of f of x itself. And in this case, f of x is x cubed minus 2x squared, right? So this is going to be e to the x cubed minus 2x squared, this quantity times 3x squared minus 4x. Okay. And fourth problem. What's d dx of sine of e to the x, make it 5 e to the x. My 4's look so much like s. My 5's look so much like s, so let me avoid that one. 4. So 4 e to the x plus tangent x. So d dx of sine of 4 e to the x plus tangent x. So it looks like we have d dx of sine of f of x, right? We don't have a simple d dx of sine x. We have something more complicated, so we say sine of f of x, and that turns out to be cosine of f of x, that is cosine of 4 e to the x plus tangent x. But according to chain rule, we need to multiply this by the derivative of 4 e to the x plus tangent x, which turns out to be the derivative of 4 e to the x. Since 4 is a constant multiple, we can pull that outside of the derivative, and so the derivative of e to the x is e to the x, so 4 e to the x, plus the derivative of tangent x is secant square x. Maybe I'll go ahead and state this one. You do remember that the derivative of a sum is equal to sum of the derivatives, right? Why do I say that? Notice we have a sum here, 4 e to the x plus tangent x. So when I say the derivative of a sum equals the sum of the derivatives, what that means is if I am required to take the derivative of a sum like this, two or more things adding up like this, I could take the derivative of each one of them, derivative of 4 e to the x and derivative of tangent x separately, and add them up. So that's what derivative of a sum equals sum of the derivatives means. Okay, we're done. I'm sorry. Let me make up another one. Let me add a little complexity to this one, as in d dx of sine of e to the 5x square Okay, d dx of sine of e to the 5x square. So the way we look at this is, we have sine of something more complicated than a simple x. So this is d dx of sine of f of x, right? So the answer should be cosine of f of x, where f of x in our case is e to the 5x square, times the derivative of f of x itself. But wait a minute, d dx of e to the 5x square, that's not a simple derivative, right? Had it been a d dx of e to the x, we would know that's d dx of e to the x is e to the x. But this is d dx of e to the 5x square. Oh, no big deal. This time we have e to the f of x. So we'll apply chain rule once again inside this chain rule. So let me just copy that cosine of e to the 5x square, and the d dx of e to the 5x square would be e to the 5x square times the derivative of 5x square. And this is cosine of e to the 5x square. Now just to add clarity as to what are multiplying, this cosine of e to the 5x square, that quantity is separate, and that is multiplying this quantity e to the 5x square, and finally d dx of 5x square is simply 10x. Right? There you go. Let me make up another one. This is somewhat interesting. How are we supposed to deal with something like, say, d dx of sine cube of x? If you say, well, d dx of sine x is cosine x, so d dx of sine cube x should be cosine cube x. Wrong. Okay, so let me state that d dx of sine cube x is not equal to cosine cube x. Okay, though I will write that. Let me clearly state this. Though d dx of sine x is equal to cosine x. So now the question is, how in the world are we supposed to deal with d dx of sine cube x? And let me show you. The way you interpret any trig function which is raised to a power other than 1, such as this one, is like this. Sine cube x, do you agree it's the same as sine x the quantity cube? So you must either write it that way, or if you can think of it in your head that way, that's fine. So d dx of sine cube x is d dx of sine x the quantity cube. And now what does this look like? Would you agree that this looks like d dx of f of x raised to n, with f of x being sine x? There you go, that's the idea. Therefore, this derivative should be 3 times, applying the power rule, sine x the quantity square. Thus 3 times the quantity sine x square, which is the same as sine square x, but I'm trying to stay consistent with that notation, sine x the quantity cube. Well, are we done? Obviously not. We must make sure to multiply this by d dx of f of x itself, where f of x happens to be that sine x. So let's make sure to multiply this by sine x. As a result, we'll get 3. Now I'm going to change that sine x, the quantity square, to sine square x, times, we know d dx of sine x is cosine x. Cool? That's the idea. Along those lines, now let me make up a slightly more complicated problem. What is d dx of tangent to the power of 5 of x square plus 3x? Complicated enough? Okay. As soon as we see this, like I said before, this is a trig function being raised to a power of 5, a power other than 1. So that means we will look at this as d dx of tangent of x square plus 3x, the quantity raised to 5. Okay, now we look at it as f of x to the power of 5, which is 5, the derivative would be 5 times f of x, that is tangent of x square plus 3x raised to a power of 4, right, nx to the n minus 1, times the derivative of tangent of x square plus 3x. See, this way I am unraveling things in a very slow and methodical fashion, one by one. I can replace this with a tangent to the 4 of x square plus 3x, and d dx of tangent of something. This is not its d dx of a simple tangent x. This is d dx of tangent of something more complicated. So we apply chain rule again, and derivative of tangent x, d dx of tangent x is secant square x. Therefore, this must be secant square of x square plus 3x. We are not done, because we didn't have a simple tangent x. We had something more complicated. We better multiply that more complicated, the derivative of the more complicated thing, like that, right? And this ought to be the final step. 5 tangent to the 4 of x square plus 3x times secant square of x square plus 3x times the derivative of x square is 2x and that of 3x is 3. That's it. Now, let me throw a small challenge for you. I'm pretty much done. I ask my students all kinds of really complicated ones. For example, I ask them, what's d dx of e to the sine cube of tangent squared 7x square plus 9x, or even more complicated ones. Do you think you can handle this? I'll leave it to you. Maybe it's unfair to leave it like that. Let me at least write down the answer, and you can do either step-by-step method or in one shot, but I'll do it in one shot. Okay, you can check your answer. I think this is going to be e to the sine cube of tangent square of 7x square plus 9x times 3 sine square of tangent square of 7x square plus 9x times cosine of tangent square of 7x square plus 9x okay, now the derivative of tangent square x should be times 2 tangent x, 2 tangent of 7x square plus 9x, because I had a tangent square. What else? Times secant of 7x, secant square of 7x square plus 9x. Am I finally done? 14x plus 9. Let me take a look at that. So d dx times of that is e to the sine cube, okay, 3 sine square of that times the derivative of sine itself, which is cosine, and 2 tangent of that, the derivative of secant squared. That should be your final answer. Cool. I hope it helped you.